My name is Adiels, and I will give a brief overview of our paper with the title The Construction of New Masonry Bridges, inspired by Paul Séjourné, written together with my supervisor, Professor Chris Williams. Séjourné was a French civil engineer, and is mostly known for his innovations in design and construction of masonry bridges that were built during the first half of the 20th century. And many of his bridges are still standing today. Historically, Séjourné's work may have been overshadowed by other well-known civil engineers active at the same time, such as Maillard and Vierendeel, who both pushed the design of bridges in materials that are still considered more modern in steel and concrete. However, Séjourné wrote maybe one of the most extensive works in 6 volumes on masonry bridges and arches, Grand Bout, and also an article on 50 years of progress in the art of designing and building large masonry bridges in 1930. Séjourné writes some advantages of masonry compared to concrete in being able to predict the crack patterns and the ease of repair. In concrete, it is difficult or impossible to predict cracks and repair it, he states. However, since the First World War, the manpower has become scarcer and more demanding and less good, he continues. And there are few apprentices, thus making it difficult to build good masonry bridges. Thus, why would there be a future for new masonry bridges, since they are considered expensive to build, and our knowledge and skills relating to the design and analysis and construction of these bridges are still limited. However, there are aspects concerning sustainability that might make us reconsider masonry bridges. One such aspect is that many masonry bridges, such as the Maidenhead Railway Bridge, are still in use and have performed well over time and require relatively little maintenance compared to modern bridges. And if one looks inside, many of these bridges contains quite a lot of fill material between the arch and the spanner walls. It can be earth, soil, or stones. At least in Sweden, there is a debate regarding how to handle fill material generated during large infrastructure projects. Using it in the design and construction of new masonry bridges could be one option. The fill spreads the load from the road on the arch, and the weight of the fill stabilizes the arch. So from this perspective, the more fill the better. On the other hand, from the point of view of foundation, the less fill the better. So it will always be a compromise. How does the fill affect the form of the bridge? If we assume that the load from the fill on the arch is hydrostatic pressure, and we ignore the weight of the arch in comparison to the fill, then the curvature of the arch must be proportional to the vertical distance. The shape of the arch should therefore be that of Euler's elastica. This is also illustrated by Rankine in his famous book, A Manual of Applied Mechanics. Thus, the elliptical-shaped arches with increased curvature near the supports to balance the load from the fill, seen at the Maidenhead Railway Bridge, and to the right, a bridge by Séjourné. The knowledge regarding hydrostatic arches is well known. However, the objective of this paper is to derive the shape of the hydrostatic shell, combining the arch and the spanner wall. Starting from the memory theory in general coordinates, assuming hydrostatic pressure from the fill, we then align the principal stresses with the geodesic coordinates, which is a special type of curvilinear coordinates on a surface, where the coordinate curves are geodesics in one direction and orthogonal trajectories in the other. With those geometrical constraints on our grid, we can reformulate the equilibrium equations for our membrane shell. We have solved this numerically, generating the geometry by starting from a chosen cross-section in the middle, perpendicular to the span. Then one can calculate the necessary normal curvature of the geodesics, which is in the direction of the span, to balance the load from the hydrostatic pressure. Since the principal stresses are aligned with the geodesic coordinates, meaning the orthogonal trajectories are equally spaced, similar to bed joints in a masonry or brick vault, which can be a useful feature for fabrication and construction. In this study, we have looked into the works of Paul Séjourné and Burnell regarding masonry bridges interacting with the fill. We have investigated the optimization of bridge geometry to carry the approximately hydrostatic loading from the fill. However, the form finding is only the starting point in the design process, followed by further analysis considering more load cases and actions on the structure. Possible future studies include investigating geostatic arches and shells and performing experiments on physical models and prototypes to give more insight into the structural behavior and construction of these bridges to develop our concept further. Many masonry bridges designed and built more than 100 years ago are still in service, carrying trains, cars, and people. They have often proven more durable and more economic to maintain than modern bridges. Thus, masonry bridges can be considered sustainable structures in this regard. And civil engineers of today and the future have the challenge of working with local resources to produce durable solutions. Hence, designing efficient structures utilizing soil or fill is one of the viable alternatives to contemporary practice for sustainable civil engineering for the future. With that said, perhaps we should now revisit Paul Séjourné's work to see if we can start building masonry bridges again. Thank you for listening.